Welcome back. In this video, we are going to learn how to derive a general expression of reversible thermodynamic work, that is PV work or pressure volume work required to be done on a closed system such as a piston cylinder assembly containing some gas from the first principle. Then, from that general expression of reversible thermodynamic work, we will learn to further deduce the expression of work for the case of an ideal gas to change its pressure and volume from one state to another in an isothermal process. In other words, we will start with the most fundamental definition and form of work done by an external force on a system to deduce a general expression of reversible thermodynamic work done on a closed system that contains some gas. And for the specific case of an ideal gas, when its pressure and volume change from one state point to another in a isothermal process, we will further transform the expression of the work accordingly while applying first the relation between the pressure and the force that the pressure exerts on a plane surface. Second, the properties of reversible process. Third, the formula of the volume of the cylinder in terms of its cross-sectional area and its length. Fourth, the properties of an ideal gas and an isothermal process. Since we are going to use this question as a learning reference, which is from GATE 2013 MESET A, let's first read out this question and try to analyze and understand it for what is given and what is asked. A cylinder contains 5 cubic meter of an ideal gas at a pressure of 1 bar. Alright, so the cylinder initially contains an ideal gas at a pressure of 1 bar and a volume of 5 cubic meter. Alright, let's move further. This gas is compressed in a reversible isothermal process till its pressure increases to 5 bar. So this gas which is contained in the cylinder is compressed in a reversible isothermal process until its pressure increases to 5 bar. Alright, now let's move further. The work in kilojoule required for this process is, Alright, so the question asks about the work in kilojoule required for this process, alright, which is compression of the ideal gas in a reversible isothermal process. Alright, now let's begin by considering a piston cylinder assembly containing some gas which becomes a closed system. Alright, so the piston cylinder assembly containing some gas becomes a closed system. Alright, at some arbitrary pressure P. Alright, so the pressure of that gas is P. Alright, and drawing the side section view of this system. Alright, so let's draw the side section view of this piston cylinder assembly containing some gas at an arbitrary pressure P. Alright, so we have the side section view of the piston cylinder assembly containing some gas at an arbitrary pressure P. Alright, here we can assume that first the piston is massless as its mass is not relevant in this scenario. Second, an external force F is applied on the piston. Third, no pressure exists over the external surface of the piston. Fourth, the internal cross-section area of the cylinder is A, which is also equal to the circular area of the piston. Alright, so these are the general basic assumptions in our case. Alright, so what we will do here is we will try to derive the expression of the work W done by the force F on the piston, which will be equal to the work done by the piston on the gas. Alright, so we will try to derive the expression of the work done by the force F on the piston, and this work will be equal to the work done by the piston on the gas, because the entire process is reversible or quasi-static, that is, no friction exists between the piston and the internal wall of the cylinder. Alright, so in a reversible process or quasi-static process, no friction exists between the piston and the inner wall of the cylinder. Alright, second, the piston almost always remains in static equilibrium. Alright, so this piston, as it moves in the vertical direction, almost always remains in static equilibrium, meaning the net force on this piston almost always remains equal to 0 in the vertical direction as it moves inside the cylinder. Alright. Third, the movement of the massless piston is extremely slow, resulting in the thermodynamic properties of the gas inside the cylinder, such as its, its pressure P and its temperature T, remain the same everywhere inside the volume of the cylinder at any particular instant. Alright, so due to the reversible or quasi-static process, the movement of the piston in the vertical direction is so slow that the thermodynamic properties of the gas, such as its temperature and pressure, remain the same everywhere over its entire volume. Now, let's suppose that the piston is at some arbitrary position x with respect to the bottom end of the cylinder, and the piston moves a differential displacement dx in the upward direction. Alright, so we have the diagram where the piston is at some arbitrary position x with respect to the bottom of the cylinder, and the piston moves by a differential displacement dx in the upward direction. Alright, then the corresponding differential work dw done by the force F, which can be assumed to be unchanged along with the pressure P during the differential displacement of the piston, is given by this expression. Alright, minus F times dx. Alright, because the work done by a force on an object, which is the piston here, is equal to the force times the displacement of the object in the direction of the applied force, and the negative sign here indicates that the force F acts in the opposite direction of the piston's displacement dx. Alright, so using the basic definition of the work done by a force, we get this expression of the differential work done by the force F on the piston when the piston displaces by dx in the opposite direction of the applied force F. Alright, so that is why the negative sign. Since the entire process is reversible or quasi-static, the net force on the piston must always be zero Alright, so because the process is reversible, that is quasi-static, the net force that acts on this piston in the vertical direction must be zero, which means this force F must be balanced by the force that this gas exerts on the bottom end of the piston in the upward direction. Alright, now let's move to the next page. In other words, the downward force F on the piston must be balanced by the upward force, which is a pressure force PA, that the gas inside the cylinder exerts on the inner plane surface of the piston. Alright, so the gas inside the cylinder exerts the pressure force PA on the inner or the bottom end surface of the piston in the upward direction. Alright, as we can see here that this gas exerts the force PA, where P is the pressure of the gas and A is the cross-sectional area of the piston. Alright, and we know that the pressure force due to a pressure on a plane surface is equal to the pressure times the area of that plane surface. Alright, so the gas inside the cylinder exerts the pressure force PA on the inner surface of the piston in the upward direction. Alright, and this force is equal to P times A. Alright, therefore let's replace F with P times A in differential work expression, which is in the previous page. Alright, so after replacing F in this expression, we get this expression. Alright, because the applied force F is equal to the pressure force PA. Alright, and that makes the piston to remain in a static equilibrium. As we know that the differential displacement of the piston causes the differential change in the volume of the gas inside the cylinder. This differential change in the volume dV of the gas inside the cylinder is equivalent to a volume of a cylindrical body of cross-sectional area A and length dx. Alright, so the differential displacement of the piston by dx causes a differential change in the volume of the gas. Alright, and this differential change in the volume of the gas is equivalent to a cylindrical body of cross-sectional area A and length dx. Alright, so let's replace A times dx with dv. Alright, in this expression. Alright, so after replacing A times dx with dv, we get this expression. Alright, because we know that the volume of a cylindrical body of cross-sectional area A and length dx is equal to the multiplication of its cross-sectional area and its length. Alright, to obtain the expression of the total reversible thermodynamic work W done on the gas by the piston or the surroundings, let's integrate above expression on both of its sides and apply the limit for the volume V of the gas when its volume changes from initial volume Vi to the final volume Vf. Alright, alright. So after integrating this expression on both of its sides and applying the limit for the volume, we get this expression. And then we integrated this term and get this expression of the total reversible thermodynamic work done on the gas. Alright, and this negative sign here indicates that the work is done on the gas. Alright, and if we remove this negative sign, then we would have an expression of the work done by the gas on the piston or on the surroundings. Alright, so this is the expression of the total reversible thermodynamic work for the closed system. Alright, and here this negative sign indicates that the work is done on the system. Alright, and if we remove this negative sign, then this would indicate that the system does work on the surroundings. Alright, since the gas is an ideal gas as given in the question, let's apply the ideal gas relation which is given by this expression. Alright, and replace P with this term in the expression of work. Alright, so the gas inside the cylinder is an ideal gas. Alright, so we will apply the ideal gas relation which is given by this expression: pressure times the volume equal to mass times the characteristic gas constant of the ideal gas times the temperature. All right. And then we will replace P with this term in this expression. All right. All right. So after replacing P with this term, we get this expression. All right. As the compression process of the ideal gas is isothermal, that is, temperature remains constant, the term becomes a constant and can be taken out of the integral. All right. Since the temperature of the ideal gas is constant, we can take out this term m times r times t from the integral. All right. Because the cylinder piston assembly is a closed system, so the mass of the ideal gas inside the piston cylinder assembly does not change, and R is the characteristic gas constant of the ideal gas, which also remains constant, and T is also constant because of the isothermal process. So we can take this term out of this integral. All right. All right. So after taking the constant term out of the integral, we get this expression. All right. Now we will integrate this term using the standard result. All right. All right. So after integrating this term, we get this expression. All right. Where we used the standard integration result. All right. And this is ln b. All right. Now let's apply the limits. All right. So after applying the upper and lower limits of the volume V into this and subtracting, we get this expression. All right. Now we will simplify this term using the property relation of the logarithmic function. All right. All right. So after applying the property relation of the logarithmic function to this term, we get this expression. All right. Now we will use the ideal gas relation to simplify this expression of the work. All right. All right. So after using the ideal gas relation and the isothermal property, we replaced this term with this term because this term is constant because of isothermal condition, and from this ideal gas relation this term becomes constant, that is, the product of pressure and volume is a constant. All right. So we can write this term also as P initial times V initial. All right. And because this term is constant. All right. And we can also write this term as P final times V final. All right. Where Pi is the initial pressure and Pf is the final pressure. All right. And Vi is the initial volume and Vf is the final volume. All right. Now we will replace this ratio of the volume with the corresponding pressure ratio using this portion of this expression. All right. All right. So after replacing this volume ratio with this pressure ratio using this relation, which is obtained by rearranging this, we get this expression. All right. Now we will plug in the given numerical values of the initial pressure, initial volume, and final pressure in this expression along with their units. All right. All right. So after plugging in the numerical values and the units of the pressure and volume in this expression, we get this expression. All right. Now simplify this ratio and use the fact that 1 bar is equal to 100 kilopascal. All right. All right. So after simplifying this ratio and using the fact that 1 bar is equal to 100 kilopascal, we get this expression. Now we will further simplify this expression using the fact that the product of kilopascal and meter cube is equal to kilojoule. All right. All right. So after simplifying the unit of this expression, we get this expression. All right. Now we will plug in the value of this ln 0.2 and simplify the calculation to obtain the value of the work. All right. So after plugging in the value of ln 0.2, we get this expression. All right. Now we will simplify its calculation and solve for the value of the work done. All right. All right. So after simplifying the calculation of this expression, we get the final value of the work done, which is this. So from the given options, the correct option is this option A. All right.